Alright, today we're talking about surface area and volume of spheres. So spheres are basically a ball, and geometrically we define it as the set of all points in space that are equidistant from a given point, called the center. So very similar definition to what we had for a circle. The differences are, instead of being equidistant in a plane from a center, we're equidistant in space. So 3D circle. A chord, just like for a circle, is a segment whose endpoints are on the sphere. A diameter is a chord that contains the center. So these definitions are exactly the same as they were for a circle. A new thing we have is this concept called a great circle. A great circle is the circle formed by a plane that cuts through the center of a sphere. So to kind of illustrate this, I want to look at Onshape and show you some ideas. But first, let's do our last definition. Hemisphere are two congruent, not the two, just two congruent halves of a sphere which contain the center. So kind of like the northern and southern hemisphere or eastern and western hemisphere, right? So we can split a sphere with infinitely many planes. As long as they go through the center, they're going to form hemispheres. Okay, so let's look at Onshape real quick. And I want to create a sphere. So I'm going to make a sketch of a circle. And I'm going to make a dividing line vertically through the center down the middle and get rid of half of this circle. Then I'm going to use an operation called revolve to spin this around this axis. So I'm going to revolve this shape around this central axis, and it's going to create a sphere. So now we have a sphere, and what I want to look at is taking a plane, and we're going to make an offset plane here. And that's fine, we'll put it there. So notice that wherever this plane cuts through the sphere, we end up with a circle where they intersect. So if I basically cut off everything, I can actually do that. So let's split this sphere with that plane. And then just get rid of this part. Nope, not that whole thing. Just this part. So we end up with a circle. So imagine if this sphere were just the points that form the outside of it and not a solid sphere, that we would just end up with this circular profile right here is where the plane and the sphere intersect. And the closer I move the plane to the edge of the sphere, the smaller that gets. So if I move it here, I'm going to end up with a much smaller circle. And if I moved it all the way to the point of tangency, I would be intersecting the sphere at a single point where the plane and sphere are tangent. Now, on the other end, if we move toward the middle, so if I take this plane and I move it toward the center of the sphere, then this circle gets bigger and bigger until its diameter is basically the same as the diameter of the sphere itself, or is double the radius of the sphere itself. So whenever we have a circle like that, that's formed by a plane crossing through the center of the sphere, so whenever this plane passes through the center of the sphere, the circular profile that's created right here is called a great circle. So a great circle is any circle that goes around the surface of a sphere that its diameter is double the radius of the sphere, meaning that it lies on a plane that passes through the center of the sphere. So I just wanted you to kind of see a visual of how the position of this plane can create bigger or smaller circles. Let me get another visual real quick to show you. So you've probably seen in science or somewhere that we divide the Earth into lines of latitude and longitude. So these lines of latitude that go east to west, like the equator, are basically like that plane that I was moving from the center of the sphere out toward the edge. So the equator is a great circle of the Earth, but all of our other lines of latitude have smaller diameters because that plane is parallel to the equator, but moving out toward the north or south pole. So those circles' diameters are getting smaller and smaller as they go. Whereas lines of longitude, which basically go north to south, like the prime meridian, these are all great circles. So you could think about it as a plane slicing through north to south and then basically rotating that plane around the axis at the center of the Earth. So all lines of longitude are great circles. They all have the same diameter, which is double the radius of the Earth, whereas all of our lines of latitude have varying radii. So just a kind of frame of reference of where you might have seen some of these ideas before. All right, so let's talk about formulas. We love formulas, right? So surface area for a sphere is one you probably have seen before. It's 4 pi r squared. And then if we take a hemisphere, you might think, oh, that's just half of the sphere, right? But when we cut a sphere in half, so let's go back to our on-shape picture. When we cut a sphere in half, we have this outer face, but we also have this top face, or the face where it's split. So we do get half of the sphere surface area right here, so that's going to be 2 pi r squared. But we also add the kind of cut face, which is going to be pi r squared, because this is, for a hemisphere, this circle has the same radius as the sphere itself. So that means that our hemisphere is going to be 2 pi r squared plus another pi r squared for that cut face. So this is the outer shell, and this is the cut face. And so together, we end up with 3 pi r squared. So kind of counterintuitive, because you think obviously it's just half of a sphere, but we have to account for that extra face in the middle. So thinking about it, like when we split a sphere into two hemispheres, we're actually creating extra surface area by doing that. Kind of like if we have a rectangle and it has a perimeter, so say this is 8 and this is 4, then my perimeter would be 24. But then if I split that down the middle and separate it into two squares that are 4 on a side, then I actually end up creating additional perimeter because this edge and this edge were not part of the original. So same exact idea with splitting the sphere. I'm adding some extra faces that weren't part of the original shape. So I end up with a bigger perimeter, which would be 4 times 4 times 2, which is 32. So very similar idea here. All right, so we have some examples. We want to find the total surface area of a basketball with a diameter of 9.5 inches. So first of all, our formula is in terms of radius. So if we want to work with that, we're going to say our radius. First of all, I would turn this into a fraction. So this is 19 halves. And then our radius is half of that. So we'll say our radius is 19 fourths. Our total surface area is going to be 4 pi times 19 fourths squared. And then we get, we're going to leave this in terms of pi. So we have 4 times 19 times 19 divided by 4 times 4, because that's 19 squared and 4 squared, times pi. We can simplify a little by getting rid of this 4. Then we need to know what 19 squared is. So I would say that's 20 times 19 is 380, but we have one fewer 19 than that, so that would be 361. I hope that's right. Sounds about right. So we end up with 361 pi, and we're talking about an area, so this is going to be square inches. So yeah, that's pretty much all there is to that. Just plug in radius. We could have also done pi d squared over 4 instead of r squared, but you know, whatever. It doesn't really matter. We end up with the same result. So we get that one. All right, so surface area, pretty simple. If we wanted to find the hemisphere area, we would do the exact same calculation. We would just do 3 instead of 4 right here, so no real purpose to doing that. All right, so volume is the space inside of a sphere. So if you're thinking about like a basketball, the amount of air that you would need to fill it is the volume. Our formula for the area of or volume of a sphere you've probably seen before. It's 4/3 pi r cubed. So we need cubic units to make volume, of course, and this is just how it works out. And you probably saw that in earlier math related to volumes of cylinders and cones and how all of those kind of interact, which is kind of neat. Volume of a hemisphere is simpler because it is what you'd expect. It's exactly just half of that volume. So we don't need to worry about faces or anything because we're dealing with volume. So we're just going to do half of that. So 1/2 of 4/3 pi r cubed. And we can combine these two fractions to end up with 4/6 pi r cubed, which simplifies to just 2/3 pi r cubed. But there's really no point to having a formula for that since it is simply half of a sphere. Just find the sphere volume and take half of that and you have a hemisphere. Okay, so they say find the volume of a sphere with a diameter of 7 feet. So d is 7, meaning r is 7/2. And we're going to use this formula right here. So we have 4/3 times 7/2 cubed times pi. So just rearranging it to put the numbers together and pi at the end. So I would think of that as trying to simplify this instead of like cubing 7 and cubing 2. We probably will have to cube the 7, but let's think of that as 4 times 7 times 7 times 7 divided by 3 times 2 times 2 times 2, and then we have our pi. So 4 cancels out 2 of the 2's. So when we simplify it, we have 7 cubed over 6. So 7 squared is 49. 49 times 7 would be 63, 28, 34, hopefully 343. So that's going to be 343 over 6 times pi, and that'll be in cubic feet because we're talking about volume. 49, yeah, that's probably right. So that's 286, yeah, sounds right. Cool, so 343 over 6. We know that doesn't simplify because we started with our kind of factored version here, and we knew the 7's and the 3 and the 2 didn't simplify, meaning that this larger combined fraction won't simplify. Find the total surface area and volume of a hemisphere with a diameter of 12. So they keep giving us diameters. So our radius is going to be 6 centimeters. And our total surface area is going to be this one, hemisphere. So half of a sphere is going to be 2/3 pi r cubed. 2/3 times the radius cubed times pi. So I'm going to think of that as 2 times 6 times 6 times 6 over 3. That way I can simplify one of these 6's into a 2. And then I end up with 12 times 12, which is 144 pi square centimeters. So I put this into, that's 6 times 2 is 12, and that 6 times 2 is 12, and their product is 144. Then if we want the volume, we just need to do our sphere volume. Oh wait, I just did the volume, right? Yeah, I did the volume. So that was cubic centimeters. So that was volume. Surface area would be 3 pi r squared. So that's 3 times, our radius was 6, so 3 times 6 times 6 times pi. So that's 36 times 3 is 108 pi, and that one would be square centimeters. So nothing too complicated here, literally just plugging into formulas, and if you forget the hemisphere formulas, you can always rederive those because they're just based on the whole sphere formula. You do kind of need to know these two, 4/3 pi r cubed and 4 pi r squared, or have a formula chart that has them on it. So the rest of the notes are just practice on that stuff, so no big like nothing really new. There's a section here that talks about great circles, which we've kind of already looked at in Onshape. So hopefully that seems straightforward enough. And then some composite volume or composite surface area here. So for this one, note that since the hemisphere is attached to this cylinder, the extra cut face that we talked about isn't actually relevant. So you're just going to have half of the total surface area of the sphere plus one base of the cylinder plus the lateral surface area of the cylinder. So yeah, that's that. There's a table here where you can practice those relationships. So I'm not going to fill all of this in with you, but just circumference of great circle. So we know that that is 2 times pi times the radius of the sphere. Surface area of sphere we knew is 4 pi r squared, and then volume of sphere is going to be 4/3 pi r cubed. So this table is a way to practice starting with different pieces of information and then coming up with the other ones. So if we're starting with the surface area, we can go back to the radius and then use that to find the missing values. So that's pretty much it, pretty simple, and formulas you probably already knew. So the main new concept here was great circles. That one you hadn't heard about, and this idea of planes and circles intersecting and forming different circles with their intersections.